Welcome back and thank you for joining me for the beginning of 7.2. Today we're going to begin talking about exploring exponential models. Now there's four main types of exponential models that we're going to be talking about. Today we're going to cover two of them, exponential growth and exponential decay. Now, as the name implies, growth, we're going to be talking about an increase by a fixed percent for each time period. Usually years, but sometimes we'll run across other ones. Exponential decay is a decrease by a fixed percent each time period. So, as we're looking at these, we're going to have that A of t represent the amount after t time periods. So usually, again, t years. And then notice our two equations. Right, these are going to be the two things that you need to know for today. Now notice they're very, very similar. What you're doing is you're taking the initial amount in both cases, but then you do a different thing with the rate. For increase, you take 1 plus the rate. For decrease, you take 1 minus the rate. And then that time becomes your exponent. Now, there is one thing that we need to know, all right? One critical detail. Notice that rate we need to use as a decimal, okay? So in every problem, you're going to see percents, okay? Because in common everyday language, we talk in terms of percents. However, in terms of mathematics, percents really aren't that useful to us. Whenever we're plugging something into an equation, it's more useful to understand it as a decimal, all right? So, what are we going to do with these? Well, we have a couple steps. Now, the first step is very, very critical to understand the vocabulary. Okay, there's certain words that will indicate growth versus decay. And you need to be able to identify those words because later on, when we're using that equation in each problem, you have to make sure you're using the right equation. So after we identify that vocabulary, you're going to identify A and R, that initial amount in that rate. You're going to plug it into the equation. You're going to find the appropriate value for t. So how many time periods have passed? Plug it in and you'll be good to go. All right. So let's start our first example, shall we? So a car loses value as soon as it is purchased and driven off of the lot. You buy a new Ford sedan for $12,400. If it depreciates by value or in value by 11% each year, how much will it be worth in 5 years? All right. So first things first, identifying vocabulary to make sure we're using the right equation. Well, I see the word loses value. It depreciates. So both of those are going to be referencing decay. Okay, this is an exponential decay problem. And again, I can tell because of that vocabulary. Now, the next two things I need to identify. I want to identify that A value. The A value is the initial amount. So A is going to be 12,400. And then I need my rate, my R value. So 11%. But again, it's not useful to us as a percentage. We need it as a decimal. So I'm going to take that decimal spot and I'm going to move it over 2 places. So as a decimal, my rate is 0.11. Excellent. So now I know that I'm going to be using my decay equation. Oh, I'm sorry. Began writing that wrong. So our A is going to be A times 1 minus R to the T power. So our A is 12,400. 1 minus R. Well, 1 minus 0.11 is going to be 0.89. And then we have to use our appropriate t value. Well, here our t is going to be 5. So I'm going to plug a 5 in. Now, if you type it into the calculator exactly as I have written, you're going to get the right answer. Okay? So when you type it into the calculator, you should get $6,924.23. That's how much the car is going to be worth in 5 years. And again, this is one of those times. Be sure to have the calculator out in front of you because you should be calculating these with me to make sure that you're typing it in right. And you should type it in all at once. You get precise answers. I don't want rounding and stuff like that because that can dramatically change your answers when you're dealing with exponents. So, let's look at our next one. Cell phone use has been increasing rapidly for high school students. A recent study showed that this year, 1,560 students at Elk River High School have cell phones, and it is increasing at a rate of 4.7 per year. How many students will have cell phones at Elk River High School in 6 years? All right, so I see the word increasing. Increasing again. So this is going to be an exponential growth situation. So once I've identified that it is a growth situation, I'm going to start identifying my pieces. So my initial value is 1,560. My beginning rate, 4.7%. But again, that's not useful to us in the equation. We can't use percents, we need decimals. So I'm going to take this, move it over twice. Now don't forget, when you have a percentage that's less than 10, that means you're getting that placeholder 0. So make sure that you're getting 0.047. Don't be that kid that tells me 0.47. All right? You need that placeholder 0. Then finally, our t in this problem is going to be 6. We're talking about 6 years. So now it's time to plug that in. So we're going to take that initial value, that 1,560. Now this time it is a growth problem. So we have 1 plus 0.047. So we're just going to get 1.047 to the 6th power. Again, if you type it into your calculator just like that, you will get the right answer. And in this case, we're talking about people, right? How many students? So in this case, it would be appropriate, and I'm going to leave with students, it would be appropriate to use a whole number. Okay? So when you're talking about people, so populations, anything like that, it's appropriate to round to the nearest whole number, okay? Because we're not going to have parts of people. All right, so Miami, Florida has reported record numbers in their growing population, a growth rate of 5.6% per year. The population of Miami is 86,400. If this trend continues, what will the population be in 10 years? All right, so I see the word growing and growth rate. So that is telling me that this is an exponential growth equation. So once I've identified that, I'm going to find my starting value. So we're starting at 86,400. Our rate is 5.6%. But again, we have to turn it into a decimal, so we're going to move the decimal place over twice. It's less than 10%, so that means we're going to need that placeholder 0. And our t we're talking about is 10. We want to know about 10 years in the future. So let's calculate this out. So 86,400. Now we're talking about exponential growth, so 1 plus 0.056 to the 10th power, because we're looking for 10 years. So we're going to type that exactly into your calculator. And you're going to get the population to be 148,989 people. Again, rounding to the nearest whole number because when you're dealing with populations, you don't want to deal with parts of people. So just round it to the nearest whole number. All right, so please make sure you have all of that written down. And now we're going to move on to one last type of word problem, okay? So exponential functions are often discrete, so meaning not this continuous where you can have parts of times and stuff like that. You have discrete values. So to model a discrete situation using an exponential model of that form, you need to find the growth or decay rate R. So here's an example. The table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynxes will there be in 2014? All right. So, in this case, we need to kind of label our variables. So, I'm going to let X is going to, well, here, I'm going to use T instead. So T is going to be number of years. And my Y is going to be number of lynxes. So it's important that you label out your variables so you know what you're calculating. The two things we're talking about is T for time and then Y for number of lynxes. Now, when you're dealing with discrete things, all right, so here we're going to use this little formula. That may be familiar to you. That is actually the formula for calculating percent increase or percent decrease. So something you might have seen before, but just not recently and not in this context. So y2 minus y1. So our y values, again, we're talking about the population. So we're finding the percent change in the population. So y2, we take the second value, subtract off the first value, and then divide by the first value. All right, so let's see how that calculation turns out. 120 minus 150 divided by 150 is negative 0.2. All right, so what this is telling me is that this is a decay problem. That's what that negative is telling me, that the population is decreasing, is going down. So, again, that negative R is telling me decreasing, that our population is going down. So, if we're trying to write the model for that, well, we need to pick out the right information still. So what's our initial amount, that A? Well, we're starting with 150. R, well, this is a weird thing. In the other ones, we haven't come across a negative R before. Now, all that R is saying is that it's a decrease. So really, inside our parenthesis, all that's saying is we know to use 1 minus that R. All right? So we're going to get a 0.8 inside there. So R was already given as a percentage or as a decimal, and it already had incorporated in the fact that it is negative, or that is a decay. Excuse me. All right. Now, the one piece that we're missing our t. That's something we haven't found yet. Well, let's look back at the original problem. So the original problem wanted to know in 2014. So if we're starting our calculations in 2003 and we're curious about 2014, that means that 11 years will have passed. All right, so I need to plug 11 into my equation. Oh, I'm sorry, and I didn't even put the 11 there like I was supposed to. We have to put 11 into the equation. So let's calculate this out. And again, this would be a great opportunity. You should be writing this out too. So if this trend continues, they're saying that there will only be 13 lynxes left after 11 years have passed. Again, if this model continues, that is what it's saying. All right, so thank you so much for joining me for this video. So please make sure that you have all this written down, then come back to class ready to do our practice work.